wanna pop a bottle off of ya. Chain swinging, clang clang, and it costs a lot. Bitch, I'm always at the guala, yeah, and you are not badass beat. Keep on going till you hit the spot. Whoa, I'm a big bag hunter with the bow. She got a big bed, drop it low. Mama called me and she happy with the grow. Never ever fall for a party that's a no.
Just pop the Kenny about a million options. So the stock and I stop doing the green and I'm rock.
One kiss is all it takes.
Falling in love with me.
Written by Thomas Hansen and friends with the title Regioselectivity of epoxide ring opening via SN2 reaction under bases and acidic conditions. Here, the author analyzed the quantum chemistry of the ring opening reaction of a non-symmetric 2,2-dimethyl epoxide model under bases and acidic condition using density functional theory on OL/PTZ2P. Epoxide are important functional group in synthetic chemistry. Their easy availability and ability to react with a variety of nucleophiles including simine, amine, and amine nucleophiles, hydrides, and halides make epoxide valuable and versatile substrates in various organic transformation. For this reason, these species are often used as synthetically generated valuable target molecules, including complex natural products for medicinal and biochemical purposes. In this journal, it is explained that the reaction conditions used for the opening of the epoxide ring have a very strong impact on regioselectivity. Performing the reaction on a basis will cause nucleophile attacks on the less substituted epoxide site, and conversely, if the reaction is carried out under acidic condition, the most substituted epoxide site will be attacked. So, for that explanation, in the journal, to simulate basis condition used OH mean as a nucleophile so as to obtain two products as explained before. If in base condition, the nucleophile will attack the least substituted site, so it can be concluded that this right-hand structure is more favorable. While the reaction under acidic condition with H2O as a nucleophile also produce two products, and the preferred product is the left one because under acidic condition the attack part is the more substituted part.
I want to explain about methodology for deformation and thermochemistry. This one is the Fourier deformation density. Fourier deformation density is how the slide are displayed the point in the Fourier pattern and the format are deformed. The Fourier pattern is formed by dividing a region into cells. Each dominated by a single center point. The deformant density reflects the extent to which the cells are deformed or distorted from the ideal Fourier shapes. The higher the deformation density, the greater the shape change that occur in the Fourier cell. We can know the atomic turn distribution is analyzed using the Fourier deformation density or FDD method. The FDD method partitions space into so-called Fourier cells, which are no overlapping regions of space that are close to nucleus compared to other nuclei. The charge distribution is determined by taking a fictitious promolecular as a reference point, where the electron density is just a superpositive of the atomic density. The change in density is a Fourier cell when switching from this promomolecule to the final molecular density of the interacting system in attribute to the atomic charge FDD key. The atomic charge FDD key A of atom A is calculated by the following formula. In this formula, are to FDD key A. And don't forget to this note. If positive atomic charge Pr corresponds to electron loss, and if negative atomic charge Pa corresponds to the gain of electron in a Fourier cell A. Okay, chemistry is a branch of chemistry that studies the energy change that occur during reaction. Thermochemistry is a branch of chemistry that studies the energy change that occur during a chemical reaction or phase change of a substance involves analyzing thermal concepts such as enthalpy, entropy, and give free energy to understand the energy characteristic of a chemical system. And then bond enthalpy is the energy required to break a chemical bond in 1 mole of a gaseous compound. If a chemical reaction involves bond formation, energy is released and the bond enthalpy is negative. Conversely, if a bond is broken, energy must be supplied and the bond enthalpy is positive. This is a formula enthalpy. You can look this.
Next is computational details. All density functional theory (DFT) calculations were performed using the Amsterdam Density Functional (ADF) 2017.103 software package. For all computations, the generalized gradient approximation (GGX) chain correlation functional (OLYP) was used, which consists of the optimized exchange OPTX functional proposed by Handy and coworkers. Very good. Geometry were optimized without symmetries constraint. All calculated stationary points have been verified by performing all vibrational analysis to be energy minima. No imaginary frequencies or transition states, only the one imaginary frequency. The character of the normal mode associated with the imaginary frequency of the transition states has been analyzed to ensure that it is associated with the reaction of interest. Aqueous solvation was considered in the computation using the Cosmol implicit solvation model. Solvent effects were explicitly used in the solving of the SCF equation and during the optimization of the geometry and vibrational analysis. The potential energy surfaces of the studied epoxide ring opening reaction were obtained by performing intrinsic reaction coordinate calculation, which in turn were analyzed using the PyFrac program. The optimized structure were illustrated using CYL view. Next is activation strain and energy decomposition analysis. The activation strain model, or ASM, of chemical reactivity, also known as the distortion or interaction model, is a fragment-based approach in which the energy corresponding to a chemical reaction, the potential energy surface, can be described with respect to and understood in terms of the characteristic of the reactant's procedure. In this model, we decompose the total energy delta A into the respective total strain and interaction energy, delta E strain and delta E int, and project these values onto the reaction coordinate. In this equation, the total strain energy, delta E strain, is the penalty that needs to be paid in order to deform the reactant from their equilibrium structure to the geometry they adopt during the reaction at point of the reaction coordinate. The interaction energy, delta E int, account for all the interaction that occur between these two deformed reactants along the reaction coordinate. The total strain energy can in turn be further decomposed into the strain energies corresponding to the formation of the epoxide ring, delta E strain, epoxide, and the nucleophile. We can see in the second equation. The equation energy between the formed reactants can be further analyzed in terms of quantitative quantum-molecular orbital theory together with canonical energy decomposition analysis, or EDA. The EDA decomposes the delta E int into the following three physically meaningful energy terms in the third equation. Herein, delta V Lstat is the classical electrostatic interaction between the unperturbed charge distribution of the deformed reactants and is usually attractive. The Pauli repulsion delta E Pauli comprises the destabilizing interaction between occupied closed shell orbital of both fragments due to the Pauli principle. The orbital interaction energy A delta E OI accounts for polarization and charge transfer between the fragments. The energy terms are projected onto the carbon leaving group or CLG distance. This critical reaction coordinate undergoes an well-defined change during the reaction from the reactant complex via the transition state to the product and is shown to be a valid reaction coordinate for studying SN2 reactions. Thank you.
Did you know that we can also just tweak the structure of alcohols a bit to make epoxide, which are essentially cyclic ethers where the oxygen form a 3-atom ring with 2 carbon atoms. That are also important when it comes to organic synthesis because they're much more reactive than the very stable ethers that we could only break down with a strong acid. Epoxide have a lot of ring strength, so they open up pretty easily. We can actually break open the ring in two ways to form two different products, through an acid catalyst reaction or a base catalyst reaction. The base catalyst reaction, there's nothing to protonate the epoxide. We've just got our epoxide and our basic nucleophile. So the nucleophile attack comes first. The nucleophile will attack the lead substituted carbon, triggering an SN2 reaction and breaking open the ring. We can add some acid in the second step, and the negatively charged oxygen grabs a proton, forming the final product. On the other hand, the acid catalyst reaction is an SN1-like reaction, involving our epoxide, an acid, and a nucleophile. Having an acid means we have a bunch of protons floating around. So first, the oxygen in the epoxide gets protonated. Then we have an oxonium ion with a positive charge. The nucleophile attacks the more substituted carbon, the one with better stabilized carbonation character, breaking open the ring. And finally, there's one more deprotonation step to give the final product. Like I mentioned before, the products of acid catalyst and base catalyst reaction are different because these two reactions can have different regioselectivity. Based on the result and discussion section of the article, we know that the nucleophilic attack at the beta position is favored in basic catalyst reaction, whereas the attack at the more substituted alpha position is preferred under acidic condition. In basic condition, according to activation strain model, preferred nucleophilic attack at the beta position attributed to a more stabilizing interaction energy. According to strain energy trend, beta position has less destabilizing strain energy than alpha subposition. From the ADA result dependency, shortening of the OH carbon alpha bond for alpha position result in a significantly more destabilizing steric repulsion together with a slightly less stabilizing orbital interaction compared to beta position. So less favorable orbital interaction for alpha position explained by higher lying acceptor orbital, pathway with less steric repulsion and slightly more orbital interaction. Beta attack dominates under a strong basic condition. In acidic condition, as you can see in figure 3a, attack at the alpha position exhibits considerably less destabilizing strain energy, weak interaction energy unable to override regioselectivity set by strain energy. According to nucleophile strain influence, water weaker nucleophilic nature compared to hydroxyl ion contributes to regioselectivity determination. So, less destabilizing activation strain at the alpha position overcome less stabilizing interaction energy. Epoxide ring opening reaction favors the alpha position, determining the least strain pathway under weak interaction or acidic regime.
We developed a novel method for the synthesis of this method involves a post-spin catalyst, a cell group exchange between carboxylic acid and 2,6-difluorobenzyl fluoride. As far as biacetan, this study is the first to demonstrate that a cell fluoride have the ability to function as a deoxyfluorination reagent. Also, the acyl fluoride is a solid reagent that is usually prepared, purified, handled, and stored for long-term use. Additionally, the synthesis costs and effort are lower than that of commercially available conventional deoxyfluorination reagents. Moreover, the study revealed that a series of acyl group chains involving carboxylic acid derivatives could proceed in the presence of only a post-spin catalyst under metal-free conditions. Further investigation on related fluorination are now in progress.